Additional requirements for IPF implementation. Purpose and role in safety function design. In addition to the core logic, sensors, logic solver, and final elements, every IPF includes a set of supporting design and operational requirements that ensure the function performs reliably and predictably in real plant conditions. These additional requirements define how the IPF behaves in different operating modes, what constitutes a safe state, and how specific performance or reset characteristics must be handled. They are essential for ensuring consistency with the overall safety philosophy, compliance with SILE targets, and compatibility with plant operations. Definition of the safe state. Each IPF must clearly define the safe state it is designed to achieve. This is the condition of the process or equipment after successful IPF activation, such as isolated flow via closed valves, depressurized vessel or system, rundown stopped or bypass initiated, fuel or heat source shutdown. The safe state description must reflect both the process objective and the physical end condition that ensures hazard mitigation. IPF applicability across operating modes. Not all IPFs are required or active in every operational mode. It must be specified whether the IPF is applicable during startup, normal operation, shutdown, foreseeable abnormal conditions, e.g. loss of utility, flare system limits. Mode-specific IPFs must be clearly identified. For example, certain protections may only be required during startup while others are continuously armed. This information supports proper system arming and interlock logic, functional relationships between inputs and outputs. Each IPF must define the logic relationships that connect initiators to final elements. This includes voting schemes, e.g. 1002, 2003, conditional logic, e.g. and/or gating, permissive or interlock conditions, delays, filtering, or signal validation methods. These relationships must be clear and support deterministic safety logic. If implemented in logic diagrams, e.g. FLDs or cause and effect matrices, those diagrams must be referenced. Calculation requirements. If an IPF includes derived signals or internal calculations, e.g. average of multiple sensors, delta pressure, heat flux estimation, those calculations must be documented with formulae and logic description, units and limits, source and justification for constants or thresholds. These calculations must meet the same traceability standards as control system calculations and support reproducibility and auditability. Process safety time and response expectations. For each IPF, the process safety time, the maximum allowable time between hazard detection and achievement of the safe state, must be defined. Based on this, response time requirements are specified for logic solver execution, signal propagation, final element actuation, e.g. valve stroke time. These values are used to verify that the IPF meets performance targets and can intervene fast enough to prevent escalation of the hazard. Manual reset, overrides, and bypass logic. Many IPFs require deliberate operate intervention after activation. The following must be specified: whether the IPF requires a manual reset and under what conditions it is permitted, whether operational or maintenance overrides are allowed, and how they are activated, displayed, and time-limited. The presence and behavior of startup overrides, manual shutdown capability if required for functional safeties. SEAL-rated IPFs must comply with override handling rules, including the use of maintenance override switches, MOS, for SEAL 2 functions. Failure mode behavior. The narrative must define how the IPF is expected to behave in the event of key failure conditions such as sensor failure, e.g. open circuit, drift out of range, final element malfunction, e.g. valve fails to close, logic solver fault. For each failure mode, the desired system response is described, typically fail-safe behavior, fallback logic, or alarm and operator intervention. Grouping for overrides and maintenance. If multiple IPFs share initiators or logic, the grouping for maintenance overrides must be clearly defined. This allows operators and technicians to isolate multiple related IPFs without compromising unrelated protections. Grouping is typically reflected in the cause and effect matrix through color coding or border boxes. Special alarm features. Any special alarm behaviors that support IPF functionality should be documented. This includes re-alarming behavior, e.g. persistent reminder if an IPF remains overridden, alarm inhibition during startup or override, diagnostic alarms for fault conditions in sensors or logic. Alarm settings are not included in the narrative but are stored in the project instrument database, e.g., in tools, for centralized management. Summary. These additional requirements define how the IPF operates in real-world scenarios beyond the basic trip logic. They are critical for ensuring that safety functions are not only logically correct, but also practical, testable, maintainable, and aligned with plant operations. Including this information in the IPF narrative allows for reliable implementation, effective operations, and compliance with safety lifecycle standards. Cause and effect diagrams. Purpose and function. Cause and effect diagrams provide a clear, structured view of how initiating events, causes, are linked to final actions, effects, within a safety or shutdown logic system. These diagrams are critical tools for visualizing the relationship between protective initiators, such as transmitters, switches, or logical conditions, and the devices or systems they actuate, such as valves, breakers, or equipment trips. They are used during design, verification, testing, and operational phases to ensure consistent understanding and implementation of instrumented protective functions, IPFs. CEDs serve as the bridge between process safety design and control system programming. They are used by engineers, system integrators, operators, and auditors to confirm that all protective actions are correctly linked, clearly defined, and appropriately grouped for implementation and review. Types of cause and effect diagrams. Two distinct types of CEDs are typically generated. Design CEDs, developed by the engineering contractor during the project lifecycle. These diagrams reflect the protection logic as defined during the detailed design phase. They are issued alongside IPF narratives and become part of the formal review, comment, and approval process. Design CEDs are eventually updated to as-built status following commissioning. Classification tins automatically generated by safety lifecycle or SEAL classification tools. These are used primarily as indexes or references for individual IPF assessments and typically reside within the IPF classification database or toolset. While they reflect similar logic, their structure is optimized for traceability within the CL review process rather than field implementation. Diagram content and conventions. CEDs show the logical relationship between initiators and their associated final elements. Key features include initiators, sensors or input signals that trigger the protective function. These are identified by tag number and service description. Each cause is listed vertically and associated with one or more logic outputs. Final elements, the devices or actions that respond when the initiating conditions are met. These include valve closures, pump trips, or inter-unit shutdowns. Final elements are listed horizontally, described by their service and tag number. Logic matrix. An X is placed in the matrix cell where an initiator triggers a particular final element, showing the logical relationship. Multiple initiators may be required for one action, or a single initiator may result in several effects. IPF marking. Protective functions that form part of an IPF are clearly identified in the matrix. This ensures that each IPF's trip path can be easily recognized and aligned with SEAL documentation. Controller initializations. If controller reinitializations are implemented, for example, setting controllers to manual or forcing set points, they are grouped and distinguished using a different marker, e.g. I, to indicate these are not IPFs, but operator convenience functions. Presentation and formatting guidelines. To ensure usability and standardization, CEDs follow strict formatting rules. Diagrams are produced in a consistent spreadsheet format, e.g. Microsoft Excel, with one diagram per process unit. Each UZ block grouping of trip logic is displayed on a single sheet with clearly labeled inputs and outputs. The number of UZ blocks per sheet is optimized to reduce page count and improve readability. Each initiator and final element is referenced to the relevant PEFs sheet for traceability. Notes, clarifications, and special logic explanations are included as footnotes or margin annotations. UZ block boundaries are shown with lines or shading to visually group common actions. Initiators and final elements are arranged logically to minimize scattered or confusing matrix entries. Integration with other documentation. Cause and effect diagrams are cross-referenced in the IPF narratives but are maintained as standalone documents. They are essential inputs to functional logic diagrams, FLDs, system configuration in the safety PLC or DCS, verification and validation procedures during FAT and SAT, maintenance override grouping, alarm management systems, and safety lifecycle tools. Use across project phases. During the design phase, CEs are issued alongside draft IPF narratives for review. They support HAZOP follow-ups, SEAL allocation workshops, and safeguard audits. During commissioning, they are used as a reference for input-output, I/O checks, trip testing, and logic confirmation. Once the plant is in operation, they serve as a permanent reference for operators, maintenance teams, and auditors to understand how protective logic is structured and grouped. Summary. Cause and effect diagrams are foundational to the successful implementation of instrument protection systems. They provide a transparent and auditable view of how hazards are mitigated through logic-driven actions. When aligned with detailed IPF narratives and logic diagrams, they ensure consistent execution of safety functions throughout the design, configuration, and operational lifecycle. Alarm narratives, purpose and role in alarm management. Alarm narratives provide structured descriptions of process alarms that are not part of formal trip logic, but are critical for operator awareness and timely intervention. Unlike IPFs, which bring the system to a safe state automatically, alarms rely on operator response to prevent escalation of abnormal conditions. Well-documented alarm narratives support effective alarm classification, rationalization, and implementation, ensuring that every alarm serves a clear operational purpose and contributes meaningfully to process safety and efficiency. Alarm narratives also serve as a foundation for alarm system configuration and as an input to the alarm management lifecycle, including settings validation, training, and compliance with industry standards, e.g. IEC 62682 or ISA 18.2. Scope and applicability. Alarm narratives are required for all operator actionable alarms with the exception of trip alarms, which are covered under IPF narratives and logic, pre-alarms, which are used to alert of impending trip conditions but are not treated as operator-controlled protective layers. Each alarm is documented individually even when multiple alarms originate from the same instrument, e.g. a transmitter with both high and low limits, because each condition typically demands a different response and serves a different operational role. Narrative structure for each alarm. Each alarm narrative contains the following elements. Purpose of the alarm describes the process condition being monitored and why the alarm exists. This includes the deviation or abnormal state the alarm is intended to signal, e.g. high temperature indicating potential fouling, low flow indicating a blockage. The purpose should not simply restate the condition, high level, but explain its relevance to process stability or equipment health. Consequence of no action explains what would likely happen if the alarm is ignored or not acted upon promptly. This includes possible effects on product quality, e.g. off-spec material, equipment damage, e.g. pump cavitation, overheating, process safety, e.g. buildup of pressure or risk of release, environmental or regulatory compliance. This helps prioritize the alarm and determine whether it requires immediate attention, planned response, or escalation to automated shutdown. Type of operator activity required defines what category of action the operator is expected to take, such as corrective process adjustment, e.g. reduce feed rate, start or stop equipment, notify maintenance, monitor for further changes. This categorization supports prioritization and alarm class definition during configuration. Most likely required operator action specifies the typical expected operator response in most situations, i.e. 80% of the time. This helps operators respond confidently and quickly when the alarm is activated and supports alarm training and procedural alignment. Less likely required operator action describes any secondary or alternate actions that may occasionally be required depending on operating conditions, i.e. 20% of the time. This anticipates variation in process behavior or upstream-downstream conditions. Treatment of operational messages. If an alarm condition does not lead to an operator action or only rarely does, this should be explicitly stated, e.g. no operator action, informational only. In such cases, the alarm may be reclassified as an operational message or suppressed to reduce alarm flood and improve operator focus. Alarm classification and system integration. During the implementation phase, alarm narratives support classification by helping assign alarm priority, e.g. high, medium, low, Alarm category, e.g. safety, equipment protection, environmental, operational. Suppression rules or filters, e.g. based on mode of operation. All alarm settings, such as limits, deadbands, delays, and priorities, are maintained in the plant's instrument configuration database, e.g. InTools or Delta V database, not in the narrative. However, the rationale for settings and categorization originates from the alarm narrative. Life cycle and operational use. Alarm narratives are developed during the definition phase, with completion of consequence and purpose statements. Operator actions and classification details are finalized during the implementation phase, once the full system design and process operation plans are in place. The completed alarm narratives serve as input to DCS configuration and graphics development, training material for console operators, documentation for alarm audits, HAZOP follow-up, and alarm rationalization reviews, referenced during incident investigations or near-miss analyses. Summary: alarm narratives define the role and expectation of operator response for each alarm in the system. By clearly stating purpose, consequence, and recommended actions, they ensure that alarms are meaningful, actionable, and aligned with safe and efficient plant operation. Properly implemented, they reduce nuisance alarms, improve operator focus, and contribute to a safer and more stable process environment. Functionality overview narrative, purpose and role in integrated control design. The functionality overview narrative is developed to describe how multiple interconnected control and protection subsystems operate together as a single coordinated application. These subsystems often span across vendor-supplied equipment and plant-wide automation platforms, such as DCS, PLCs, turbine governors, compressor controls, and vibration monitoring systems. The overview narrative provides a top-down description of how these elements integrate to achieve a unified control or protection function, ensuring consistency, reliability, and operational clarity. This document is essential where complex machinery, e.g. gas turbines, compressors, variable speed drives, relies on distributed intelligence and segmented responsibilities between vendors. It ensures all functional interactions are documented, understood, and validated through commissioning and operations. Scope and applicability. The functionality overview narrative is required when controller safeguarding logic is spread across two or more subsystems. Typical examples include compressor trains with anti-surge performance and driver control in separate platforms, generator packages with dedicated governor logic, protection relays, and power management systems, rotating equipment monitored by third-party vibration and condition monitoring systems, process skids with embedded PLCs interacting with plant DCS and safety systems. In such cases, each subsystem is typically documented individually by its vendor. The functionality overview narrative bridges these into a unified description of how they collectively fulfill a specific application objective. Narrative content and structure. The functionality overview narrative addresses the following key elements: application, purpose, and functional scope. Describes what the integrated system is designed to achieve, e.g. compressor throughput control, load shedding, machine protection. The scope includes the control objectives, safeguarding philosophy, and high-level performance sections of the overall system. Subsystem roles and boundaries identifies each participating subsystem, its control boundaries, and its functional responsibility. Examples include Speedtronic Governor manages turbine load and overspeed protection. CCC controls compressor surge and performance loops. Plant DCS provides sequencing, interlocks, and operator interface. Clear boundaries prevent duplication of functions and misalignment during system integration. SHA signal flows and control relationships. Outlines how signals, digital, analog, or communications, pass between subsystems during different phases of operation, such as startup sequencing and permissives, load control and transitions, shutdown and trip handling. Each signal is described by its role, e.g. start command, status feedback, interlock, its direction, and its participating systems. Modes of data exchange, e.g. hardwired I/O, Modbus TCP, OPC UA, are also identified. Operational phases and interaction behavior. Describes the dynamic behavior of the integrated application during initial energization and startup, normal running and load changes, emergency shutdowns or fault responses, manual overrides, or test modes. The narrative explains how the various subsystems collaborate to support each of these phases, including priority logic, handover of control, or transition points between control platforms. Fault handling and diagnostics identifies how each subsystem reports faults, what alarm behavior is expected, and how failures in one subsystem affect the overall system. This supports configuration of plant-wide alarms, trip propagation, and fallback behavior in degraded modes. Interfaces with operator and maintenance systems describes where and how the operator interacts with the integrated system, e.g. via DCS graphics, dedicated HMIs, or local panels. Includes expected feedback, control permissions, diagnostics access, and maintenance interfaces. Dependencies and configuration particularities highlights any specific configuration features needed to ensure proper system integration, such as control system time synchronization, mode switching logic, e.g. remote local, manual auto, redundancy schemes, and master-slave arrangements. These details are critical for both control vendors and system integrators. Development and ownership. The functionality overview narrative is developed by the system integrator responsible for delivering the process unit's automation strategy, typically the main automation contractor or engineering team preparing the process control narrative. It cannot be delegated to individual subsystem vendors, as only the integrator has visibility over all interactions and cross-platform dependencies. Lifecycle use. Initially drafted during the definition phase, the overview narrative is progressively refined throughout engineering, FAT, S8, and commissioning. It becomes a permanent part of the control documentation, supporting operations, maintenance, troubleshooting, and future system upgrades. Summary. The functionality overview narrative ensures that integrated control systems with multiple vendors and platforms operate seamlessly as a single application. By documenting signal flows, coordination logic, operational behaviors, and fault interactions, it enables reliable performance, reduces integration risk, and provides essential context for operations engineering teams managing complex system interactions.